Welcome back. We're writing Little Man Computer in C++ to help me learn the language. And last time we'd just about finished putting together the computer side of Little Man Computer, and I did spot one little part that we'd failed to address, and that is handling inbox values that are out of range. So I think we should address that now. So as you can see here, we just got the one, the two inbox tests, one for the value being put into the accumulator, and the other for the negative flag. But I think we should probably add a couple of extra tests just to check that we're handling the behavior correctly when the inbox value is greater than 999 or less than 0. So we shall start, as always, by writing a test. Test input handles inbox values greater than 999 using modulo. There we go. And we shall add, oh no, that's not where to put the test. We shall put the test in the same place in the order. And that's the one. And then, so we will want to assert that the inbox value is 0. Sorry, the accumulator value is 0. We're going to give it the value of 1000 in the inbox, and we're missing a computer as expected, so we'll create one. That's fine. We shall then call input, and we shall make sure that the inbox value is something out of range. That will then hopefully fail the test. Yes, it does. Expected 0, and the actual value is 1000, and we should be able to make that pass simply by just taking the modulo 1000 value here. We'll just do that. We'll do that rather than calling the mod function for now, just so we can get in a test for negativity as well. That won't automatically pass. There we go, that's now passed. And then we can just duplicate the test, and handles inbox values less than 0. So now we'll again have, this time we'll do it the other way around, so 999 should be -1, and the test needs to be included, as we usually forget to do. Handles values are less than 0. We run the tests, we find we have one failure, and again we can make that pass by using the mod function. And we've not given it a value to mod by. And so it correctly fails. And now we've made the test pass. I've just noticed we've not given the tests names, so we will do that as well. I will copy that. Let's put that in the right place. That looks correct, doesn't it? Now when we run the tests, they all pass and they all have names. Excellent. So we will check our status. That's fine. And we shall commit that. Handle inbox values that are out of bounds. There is arguably a question whether we should have set the negative flag on negative inbox values, but I think given that you're not technically allowed to put an inbox value that's negative, leaving the flag as false is fine, I think. Excellent. So we've now handled add, subtract, store, load, the three branches, input, output. The halt command is handled by the little man, or will be when we've implemented a little man, and the data isn't a real operation. Good. So the next stage is to start developing the little man that runs around operating the computer. And the little man essentially performs the execution cycle. So just to recap, the process is the little man checks the program counter to find the mailbox containing the program instruction, which is initially 0, which we should probably check as well, as we've not explicitly done that yet. Although I'm not sure that's no, that is part of the computer. Let's just dive in and deal with that. And I think we shall put that at the top. Test the program counter is initially set to 0. Let's see what test. What have we done with the name? The program counter. I don't like the there. It makes it unnecessarily verbose for something that's fairly long anyway. There we go. So let's make sure we give it a name, and then we just want to assert that the program counter is 0 initially. That's going to fail to compile due to the lack of a computer. We will create one and we shouldn't need to do anything else there. No, it may be that this just works, and it turns out that it does. So there's clearly some sort of default value there. But what I might do is just set that explicitly. If I can find the header file, which is here. I wonder if we can do this, if that's legal. Yep, that looks completely fine. I just like that slightly better because it makes it completely explicit that a fresh computer has a program counter set to 0. So that wasn't a big change, but we shall commit it anyway, as it's the end of things. Where are we? Let's commit that. Make sure that the program counter is initially 0. There we go, just being completely explicit. There we go. Didn't matter too much that test didn't fail initially. We could have, in fact, we can test that test is meaningful just by doing this, and indeed the test fails. It's just worth making sure that that's the case sometimes. Good. So now we have completed the computer to our current satisfaction. We may well discover later on that we require some updates to it, but it's fine for now, I think, to move on to the little man. So we were recapping. So the little man initially checks the program counter to find which mailbox will be containing the program instruction, which we've now checked is 0 at the start of the program. We then go to the mailbox and fetch that particular instruction, and the instruction is made up of an opcode, which is the first digit and then 2-digit address values. Once we've retrieved the instruction, we increment the program counter in advance of doing any other manipulations to it via branching instructions. We then decode the instruction, which, as we just described, is taking the first digit and then the next 2 digits for the 2 components. We then fetch the data from the inbox, accumulator, or memory with the address determined in step 4. Now that's not always going to be required. So for example, there's no fetch on the input or output instructions, and similarly the branch instructions have no fetch. So it'll depend a little bit on which instruction we're using, and then we execute the instruction, and finally we branch if it's a branch instruction, or store the result in the output accumulator or mailbox. This will primarily be handled by the computer, as we've already implemented the capabilities to do that sort of thing. So the main purpose of the little man is going to be to loop through this and decode the instruction and then call the relevant operation on the computer. So that all seems relatively straightforward. The question is where to start, and I think we can probably start. The question is how much do we want to expose of the little man's internals, as it were? Because we could write an initial test that, for example, checked that the little man had some sort of public current instruction value, and we can check that that is set to the value in the address pointed to by the program counter. It feels like that's exposing a little bit too much of the little man. What we really want to do, if we possibly can, is almost just have a public run method for the little man, and then that we would try and do all of the work through that run mechanism by injecting a computer. That sounds a nicer way to do things if we can get away with it. So let us embark upon that line and see how far we get. What I want to do here, just before we start, is just put a little delimitation here. Just so we can see. I keep writing count there, that's very annoying. Just so we can see where each of the sets of tests starts and finishes. It'll just make it a bit easier to work with. So we'll have an extra blank line in between the two sets of tests, and then we will have little man tests. That's probably better. And then we'll have a place to put our... Nope, not quite. We'll have a place to put our tests for the little man. That looks okay, doesn't it? Now we could go to all the effort of putting together a sort of test fixture base class and having two test fixtures, one for the little man and one for the computer. That seems a little bit much work for now, and we may refactor to that, but I think for now we will leave it in this form, and then we will get going. Let's just check that I haven't broken anything doing that. And yes, we can now see we have some computer tests and some little man tests would be a better word there. Ooh, didn't mean to do that. There we go. So now we need to actually write the first test, and we need to find a mechanism that lets us do that. So what I think we can probably do is to test. So we have two mechanisms for testing here. We can test the state of the computer when the little man has done something, and we can test the state of the output, if you will, the things that have been put into the outbox. For now, let's start down the line of the state of the computer being a test mechanism, as I think that's going to be slightly easier. So what's the first test going to be? Let's have the first test get a value from memory and put it in the accumulator. So we're going to be gradually teasing out the parsing of the instructions here. And I don't want to. I could start with. The outbox mechanism and just have a value in the accumulator and check that that's written to the outbox. But then we're looking at having to do some sort of mocking of the input-output. Maybe that's okay. Let's do that, shall we? Let's have let's do that, yeah, because we can set up a computer very straightforwardly with a value in the accumulator and a single instruction that does the out box. Okay, so test test output instruction puts the value from memory into the out box. So there we go. And we'll do that. We will make sure we run the test. We're running into dangerous territory of name clashes there. Test little man interprets output instruction. Test little man interpreting output instruction results in accumulator value in outbox. A little bit heavyweight, but we'll go with it. At some point we might do some serious renaming of these things, but not for the moment. So, what's our assertion? Our assertion, I think, is very straightforward here, isn't it? The assert r equal, we'll go back to the standard 42, and we'll check that the outbox does that. So we have no computer, so we'll need a computer. fine. Oh, that should all be okay. It fails because we have yet to do anything with that. So the computer accumulator should equal 42, but also the computer memory element 0, which is the first instruction, should be 902, is it? Yes, should be 902. And then the computer memory, just for safety here, the computer memory 1 should halt. Otherwise, later on we'll have tests running away. Now I don't know offhand whether array defaults to zeroing or not, but we'll be explicit here so that it doesn't matter. So that should all still fail. And that's okay. So now what we need to do is we need to have man.run there, which could be quite interesting. So that's going to have, we have no man, so we'll create a man, little man. Now, can I preemptively pass the computer to the little man? I think I probably can in this instance because it's fairly obvious. Let's not overdo the pedantry of test-driven development at this stage. The granularity of the steps are very much open to necessity at the time. So now we have another class little man, and the little man has a public constructor. No, let's not overdo that yet. Let's step by step just to make sure we're doing the right thing, and we're not quite. So I need to do that, and we have no constructor, so we will create a constructor. I do not know how you create a constructor, but what I'm going to do is kind of guess how a constructor might look and see what that does. Oh yes, good. That was a good guess, but I'm just going to be a little bit more pedantic than that. We're not going to change the computer, and we might as well pass it as a reference, assuming that's how one does such a thing. Yep, excellent. So then we're just short of a run method, which does that. We're going to probably be shouted out for lack of implementation. That's good. We can generate those relatively easily. Little man, that's the constructor. Does it work? Const computer, if I can spell. Good, and void, ooh, not quite, yes, void, little man, run. Do we need to put the void keyword in there? I don't think we've been doing so far, have we? No, we haven't. So clearly that's allowed. Oh, and we've got an unused parameter. Of course we have. Let's not preempt ourselves yet, and let's just do this for the time being. Excellent. We have a legitimate failure now. So that's going to need passing, and the test should pass straightforwardly by cheating. So the easiest way to do that, there are several easiest ways to do that, but I think the easiest way for now, we can't access the computer, so that's going to require a little bit of tinkering here. Let us have a private computer. Computer, do we do that? Who knows? I'll find out in a moment. One day I'll work out what order these things are in. So, computer, possibly all sorts of memory leakage going on here. Note declare here. Error can explicitly initializes the reference member as computer. Is that not how we do it? Does that not want to be a reference? Apparently not. Might want to go and check that out later, but for now we'll let it go. And then to simply pass the test, we do that, I believe. No, we don't. What have we done wrong? What have we done wrong? We have a computer. We've called output on that computer. Are we using the wrong type of storing a parameter from constructor? How do we do this? So that's the old school way of doing it. Do we need to say it's const? Let's at least chip away at the problem. And I'll say that. So it's a reference, at least. Note. Lots of error messages here. Let's take them one at a time. So, constructor for little man must explicitly initialize the reference member computer. Declared here. No viable overload for equals. Do we have to use this? Are we getting all Java on it? So what did it say? Constructor must explicitly initialize the reference number. We shall find what that means. Oh, do we do that instead? That's perhaps a little nicer if we can do that. So. Is that what we had? I believe so. Output not viable. This argument is a const computer. Of course it is. It's not really const, is it? It's a const reference, but computer itself is not const. Let us unconst it. Let's see where that takes us. Getting a little nearer. Okay, we now have a discrepancy between the declaration and the constructor. And finally, after a little bit of learning, which hopefully doesn't end up with some sort of monumental memory leak, we get to have a little man that does the bare minimum and passes the test. And next time we shall move a bit further and hopefully a little bit faster.